Okay, good morning, everyone. I hope you had a good way to the university, even though it's so cold. For those people who are from Canada, for example, it's really usually not so cold here. This is really exceptional. The weather probably adapts to you. So the goal of this lecture is to give you a little bit of an outline of how this continuum limit works. So we have mentioned it several times during the lecture, during the spring school so far. So this is really this limit where you make a connection to the physics we currently accept or we currently learn in classes. And so this lecture is a little bit experimental because in the last spring school there were several lectures. I didn't count them exactly, but 4 or 5 or something, or 3 to 4, which really somehow talked about this topic. And this spring school we're trying to explain or to put this really in one lecture. And so the goal of this lecture is not so much to really prove something to you, but the goal is to sort of give you a feeling how it works. And the goal is also to give you sort of enough terminology so that you can find your way in the blue book which Felix has shown you. So the last book which is published, and I've also sent the link to this book to you via email. So there's some Dropbox links and it's also an archive. And the idea is really to sort of give you a guide, if you like, how to find your way in that book, how the different things connect. Maybe let's start with a very general outline. And by now you've seen this picture several times, so this would be general. Okay, so remember, I'm just going to write it down again. So we are always talking about causal Fermion systems. By now you know how they are defined, and by now you know a little bit about the inherent structures. And we're basically, the question we're always asking is, which are minimizers? Which causal Fermion systems are minimizers? And I've already said, I have already mentioned yesterday that in general there's no method to find a minimizer. So, if the thing would be if you take a look at particular examples, you could do numerics to really find minimizers. But in general, there's no method which you can do. It's the same thing as if I give you a function. So there's no general method to find a minimizer. The only thing you can do is you can basically look for where's the derivative 0. And yeah. And so the idea here is really, so let's maybe draw this picture again. Let's say this is basically the space of all CFS. This is again this intuitive picture we've seen so far. And the idea is really to say, well, we know one minimizer, and this is Minkowski vacuum. So this is what Felix has shown you yesterday. So I will just denote this by rho m informally. So this is this. So you start with Minkowski space, you take into account this regularization, and then you basically construct this causal Fermion systems. And the thing we do now, as we have mentioned before, is we now take a look at perturbations. And in this context, perturbations are always families of measures. So this would be, for example, rho tilde tau, similar to what we've done yesterday. And rho tilde tau, this is basically a family of measures. And perturbations means something like, roughly speaking, you want to take a look at the derivative as yesterday. So we have rho 0 tilde is equal to rho. And we basically look at perturbation, or this is a perturbation. Okay, and so how can we understand how this works? Maybe let's draw a second picture. So this is all on the very general outline. So let's assume this is basically sort of, I'm just going to call it physical setups or physical configurations or something like this. So the idea, this is again intuitively speaking a space where, for example, here you could have Minkowski space with Dirac spinors, yeah. And this would correspond to this causal Fermion system we have constructed so far. Yeah? So there's one way to go here, like it's always with regularization, so maybe I should add an epsilon here. And there's a way to sort of go back, okay? And so the point is that when we study variations of the measure rho here, this corresponds to variations of this physical configuration over here. So this would look like this, okay? And in fact, and in fact, so the whole idea behind this approach, maybe I'll write it down as a sentence, is, so to speak, by considering perturbations, of rho m, the correspondence, maybe I'll write it in red, so this correspondence, which I wrote down with correspondence, gives information, oops, wrong color, gives information which physical configurations close to, in some sense, so this is intuitively speaking, close to m and psi are also minimizers, or in fact extrema. Okay, so this is basically the idea we have. And the essential ingredient in all of this is, okay, I wanted to give an example. So as we have seen yesterday, one way to describe such a minimizer is to just consider, I'll give you some time. Maybe let me write it like this. And so perturbations like this, how can you describe those perturbations? So as yesterday, we have seen, so well, you could introduce an external potential into the Dirac equation. You could change the metric, which is something somehow related. Yeah, those are two examples of those perturbations. And the essential point in this whole proceeding is that in order to evaluate, I'll tell this to you in a minute in more detail, but in order to evaluate whether any measure here is a minimizer of the causal action, the only thing I need, so remember that the causal action was defined in terms of the eigenvalues of the Lagrangian. Sorry, the eigenvalues of the closed chain. And this, I'll write it down in detail again. I just want to say it verbally before I do so. And so the only thing I really need are the eigenvalues of the closed chain. But the only thing I really need to determine those eigenvalues is the fermionic projector. And I'll explain that to you in a minute. But the essential point is that the only thing I really need is the fermionic projector of those perturbations. And then I can basically go here, check the causal action, and then learn something about whether this particular variation, which I've considered, is really a minimizer. Okay. So this is like the very general outline. I know it's very rough or very, so I mean, but now we'll go a little bit more in detail. So the second part of the talk would be the Euler-Lagrange equations. In a suitable form. So the first thing to mention is that for technical reasons, we cannot ask whether those perturbations really are minimizers, but we can also only basically ask whether they are extrema. Okay, so maybe technical reasons. Okay. And then it turns out, basically, that in the continuum limit, there's a nice way to write the Euler-Lagrange equations. And in order to specify this, we introduce a variation of L of xy. And in fact, so if you look at the book, you would see that there's a kappa here, and this is this Lagrange multiplier business which Felix mentioned yesterday. But for now, we'll just ignore it. So I introduce a variation of delta xy, and now delta xy is dependent on several things. For example, it's dependent on x, on y. But if you remember how it's defined, so it is defined via the eigenvalues of the closed chain. So of this axy. And those are the eigenvalue, the closed chain is pxy times pyx. So yeah. And so that's why it makes sense to define a variation of L of xy with respect to p of xy. Okay? So informally speaking, this is not to be taken too serious. This is basically something like dl of xy with respect to dp of xy. Why do I care for this? Because, as I said, by varying basically the minima, so by either considering perturbation of the causal Fermion system here, or by considering a perturbation of the corresponding physical configuration here, I basically vary the fermionic projector. Yeah? And so I introduce this variation, how? By, as follows. So basically, I'm just going to call it, so this is just delta L of xy. This is defined, or is basically, it implicitly defines what pops up in a minute. So that's the trace over the spin space Sy. And then here I have an operator, and this is the perturbation, Q of yx, delta P of xy. And then plus another term which looks the same. Trace of Sx, and then I have Q of xy, delta P of xy, and then conjugation with respect to the spin scalar product. Okay, so this is, and the thing I define is this here, this operator Q. So I introduce this variation of the Lagrangian. And this implicitly defines, so the idea behind this equation is, so this delta, as always, is basically a shorthand for considering, so maybe I should write it like this. Maybe I should write this down. So this delta here, the delta is always, this is something like d by d tau. And now I'm at the point tau equals to 0. And now in this case, it would be L. And let me just put a tau here. I mean, the dependence of L on tau would be via the dependence of P on tau. Is this clear so far? So again, like the idea is very simple. So the idea is just to say, well, L is just a polynomial in terms of the eigenvalues, the absolute value of the eigenvalues of the closed chain. Yeah? That's what this equation defines. And I'll write it down, an expression for it, I'll write that down in a minute. So maybe I should, like, just not to lose people, let me just give you a little bit of just to explain this step in detail. So remember that we had this expression for L of xy, Felix has written that down yesterday. So this was, in the case n equals to 2, this was 1/8. And then I have the sum over I and j from 1 to 4. And then basically I have those eigenvalues. So lambda I x j minus lambda j x, xy, and then squared. Okay? So this is what you have seen yesterday. And those things here, those are the eigenvalues. I should write those. Of x times y, yeah? And then you've seen yesterday, and those is the same thing as the eigenvalues of a xy, and this thing is the closed chain. So a xy was this closed chain. Oops. And how is it? And this IXY was just defined as P of XY times P of YX. Okay? So this is like, if you look again at your notes from yesterday, this is what happened yesterday. And this equation, you can make sense of this equation either just purely in the formalism, where you have this expression for P of XY in terms of this projector and the operator X and Y. But you can also make sense of this whole expression on the side of physical configurations over here. And so we only need the eigenvalues of this. The whole action is determined once I know the eigenvalue of this. Yeah. If I know these eigenvalues, that's good. And again, so just to really make sure that I don't lose something, there's two ways to determine those eigenvalues. Lambda, x, y, j, I. There's two ways to determine those eigenvalues. If I forget about this physical part over here, if I just work abstractly in the formalism, but it's just the eigenvalues of the operator x times y. Yeah, this is an element in this curly f, and so everything, I can calculate this. This is just purely within the formalism. However, if I construct those inherent structures for causal Fermion systems, then I can describe, and one part of those inherent structure is the fermionic projector. And once I have constructed this fermionic projector, I can calculate the eigenvalues by multiplying those two things. And the nice thing about the continuum limit is that because I know that, so I'm analyzing sort of variations here, and I know that those correspond to variations here, I can just focus on determining the fermionic projector of perturbations of Minkowski here. And I know that in the background, the whole machinery works. Yeah? In the background, this would correspond to taking the corresponding variation of the fermionic projector, constructing causal Fermion systems, calculating the eigenvalues of x times y, and then checking whether, and then I get basically the same result. Is this a little bit clear so far? Or not? Is there any questions? Because I don't want to lose you. So the rest of this is really just how to carry this out, yeah? And I'll give you some, I'll explain some of the methods which you use, but the important thing is really this picture. So maybe let me just draw one more, or give one more explanation, if you like, of the same things, just to make sure I don't lose so many people. Okay, so I need those lambda, x, y, j. If I have them, I can calculate the Lagrangian, I can calculate the action for all x and y. Okay, and there's two ways basically to get them. Let me just call this one maybe the direct way. So this is the direct way. The direct way just says, well, and yeah, maybe let me just add for this explanation a tau here, yeah? So this means I want to know what the lambda x, y, j is for those variations tau. So those are the eigenvalues for variations. Eigenvalues with respect to, let me just call it like this, maybe like this, HF rho tau tilde, okay? And so the direct way is really just, I mean, consider variation, and then just calculate the eigenvalues. So the variation, this would basically give you m tau, and this is the support of this rho tilde tau, and then I can calculate the eigenvalues. Calculate the eigenvalues. But there's also another way, and we can maybe call this the indirect way. And in fact, so the story here would continue as follows. So then once I've done this, the next step is then I would like check if minimizer, check if the causal fermion system is minimizer, or is, let me just write extremum. So I can do this once I have the eigenvalues because I also know the action. And then I can basically check which equations the inherent structures satisfy. Okay. And then the indirect way, this is really what one does, just because, I mean, yeah, in general, like, yeah, just because it works, maybe. So what's the indirect way? The indirect way is basically say, use this correspondence. Use this correspondence, which I've indicated with the red arrows above. And so basically, so this correspondence, maybe to write it down again. So this is a correspondence between, let me just write it like this, variations of rho tau tilde and variations of physical configuration. So this is basically what you use. And how do we use it? And so what you basically utilize, maybe let's write it like this. This is what I've just said on the other side over here. So what you utilize is really that the spectrum, sigma of xy is the spectrum, like as usual in mathematics. So maybe let me just like, yeah, write it out so that there's no confusion. So we basically use that the spectrum of x times y is the same thing as the spectrum of axy. And as I said, so axy is just given by the fermionic projector, p of xy times p of yx. And so the essential ingredient here is that I only need fermionic projector of physical or variations of physical configurations, okay? So this is the essential part, if you like. And so since there's not much space here, I will just say it in words. So once I have this, so once I know this, that I can, so it's basically a shortcut, yeah? Instead of going through the whole machinery, I can just take a look at variations on this side, and then know that in the background the whole machinery works, and construct a fermionic projector of the variations of this side, and I'll tell you how to do this. And then, once I have it, I can just directly calculate the eigenvalues. Maybe let's just add this in here. Once I've done this, I can go over here to this point and proceed as here. Yeah? And the nice thing is, since I've directly used the fermionic projector on this side, I can immediately basically check whether, so I know already the relations between the inherent structures. Sorry? No, that was before you arrived. Correspondence is the red part here, between physical wave functions and Causal Fermion systems. Okay, so does anyone I really would like to take a little bit of time for this, because this is essentially what happens. Yeah. Yeah. Yes, because there's a perturbation which basically corresponds to, so how it works is there's a perturbation that corresponds to, let's say, a change in gravity, change in the metric, and you do it on a linearized level, so you do linearized gravity, but then you know that basically both theories are covariant, so then you basically know, okay, I have to make, to write down a covariant equation which has this linear correspondence which I've basically constructed. And then there's so it's the Einstein equations up to higher terms of R, of the Ricci scalar. And then you see that those higher terms of the Ricci scalar, they come up with factors which suppress them. So they are suppressed by a small constant, if you like. But the idea is always, basically, this is why in the following we talk a lot about just the structures we usually have in physics, because I can utilize this correspondence to really just consider, first of all, variations here. Carry all of this out, and then I can calculate the eigenvalues, and then I can go on. So maybe let me explain a little bit more what happens technically, and then just whenever you have a question, just let me know. Sorry, this is not finished yet. No, where is it? Okay, we're up there. It's okay. So I would say it like this. So even so, conceptually, it's clear what you want. You want to study which minimizers exist, or maybe even only which minimizers exist in the neighborhood. And mathematically, the setup is extremely simple. So you just have to look for solutions of those Euler-Lagrange equations in the neighborhood. Nevertheless, what you then have to do in order to get information from that is quite complicated. Okay, so we've stopped here. So we stopped here with this sort of, so what we've done now, we have now introduced a variation of the Lagrangian with respect to P. Yeah?
I have a general question about the external of CFS. Why do you use the external of CFS?
Because we're looking for minimizers of the causal action. This is the postulate of the theory. So the postulate of the theory is that physical causal Fermion systems are the minimizers of the causal action. Just a postulate. Every theory has postulates. This is just one. And this is why we are looking for extremal points. We would like to have minimizers, but we can only look for extremal points. So every minimizer is an extremal point, but not every extremal point is a minimizer. Yeah. And yeah. Yeah. Okay, so we've introduced this operator Q here. And again, the idea is Q is something like the variation of L with respect to P. And with this Q, you can write the Euler-Lagrange equations in a nice form. So before I tell you how this works, I'll just say, so if you look at equation 2.6.46 in Felix' book, then you see that this Q in the continuum limit, there's a nice expression for this Q. So this Q can be written like this. Q of xy is equal to 1/2. Now the sum over j and k going from 1, in this case to 4, because I've picked n equals to 2. And then it looks like this. Lambda xy k minus lambda xy j. And then here you have lambda xy k and the complex conjugation of this. And I'll tell you why you need that in a minute. And then you have lambda k xy. And then you have f x y k. And then you have p of x y. Okay, so first of all, what is this f? Well, this is just, we've talked about the closed chain before. So this is just basically saying, so I take a look at the closed chain. Since I consider variations, everything is tau dependent. I have a tau dependence, so I'm just considering this as tau equals to 0. And then I've said before that the lambdas are the eigenvalues, and those are just the spectral projectors. So this is like k equals 1 to 4. And then you have lambda. This is the spectral theorem, basically, for the closed chain. Lambda xy, k, and then you have f xy, k. So those are basically the eigenvalues, and those are the, if you like, the spectral projectors. I mean, yeah, spectral. Okay, so what this tells you, what this equation, which I've just written down, tells you, is there is this way to introduce the Q, and then there's just a result which follows that the Q has this form. Essential ingredient here, the Q, I can calculate the Q if I know the eigenvalues. This is again, so, and why is this sort of plausible that this is possible? Well, because the Lagrangian is just a function of the eigenvalues. So you have this Q here, it's just, you can, this Q is just an expression in terms of the eigenvalues of the closed chain. And this F here is a spectral projector, and this P here is the fermionic projector. And now the nice thing is that with sort of introducing this Q like this and taking this result about the form of the Q right here, there's a nice way to write the Euler-Lagrange equations. And this is a proposition. And this is proposition 143 in Felix' book. So it's always about the blue book, which I'm referring to. And this just says the following. Let rho, so arbitrary rho, be a minimizer. And then for the, maybe I should write this. Then, and this is not so important for us here, for a suitable choice of Lagrange multipliers. We have the following equation. So basically, the equation is, so I integrate over m, and then I have q of xy, just the operator which I've just constructed, and then I have psi u of y. This is what we have seen yesterday. This is just, so I'll write down what it is again in a minute. The rho of y. And this is equal to lambda half times the psi u, and now at x. And this equation is to hold for all x in m. and for all u in H. And this was, as yesterday, this here is really just the projection to Sy of u. Okay. Oh, and lambda is just a constant. Of Lagrange multipliers, let me just write lambda and others. So it's just a constant, basically. We'll get rid of it in a minute. So why I'm giving you this theorem, because this really, like, basically tells us what happens, or what we have to do. So yeah, let me give this a box, maybe. So this is basically a form of the Euler-Lagrange equations, which we've seen yesterday, which is very nice in the continuum limit. And I'm completely aware of the fact that, like, so there's no way in this lecture I can prove things. I can just tell you to give you a feeling about how the whole thing works. And if you want to see the proof, just look at the book. Okay, now there's several things that's happening. So on Monday, Felix has mentioned that P of x diverges on the light cone. On the light cone. So if you remember, this was this picture Felix drew, which looked like this. So I think he used red color to really tell you, well, there's divergence on the light cone of this object. Yeah. And from this it follows that also, so therefore also the basically the lambda xy, let me write it like that, xy diverge on the light cone. On LC is the light cone. And from this it follows that also the Q of x y diverges on the light cone. This is central. It's very important that this happens. Yeah, so I thought the regularization will come at the very end of the lecture. I mean, I want to explain it step by step, basically. And so therefore, what this means is basically that this equation, let's just give it a star here. So first of all, first thing is that star needs to hold. And now I would just, so we'll go into this divergence also in more detail. Needs to hold order for order, yeah? Let me just write it this, order for order. Okay, and see further later. So I will explain this in detail later. But this just means, so the thing, this divergence of x and y are both chosen if x and y are in a light-like relation. So if x is on the light cone of y, this diverges. And it diverges to different degrees. And therefore, so I just need to demand this equation for every, so going from one order to the next. So I have this degree, so there's a maximal degree of divergence. So maybe just to, so let's use, maybe let me write it like this. So let's, psi will just be defined as y minus x. Okay, and so basically what happens is that Q of xy is a sum where I have one term which goes 1 over xi squared, and then this to a power of, let me just call it p. Yeah? And then there's some term, and then there's a term 1 over xi squared, and then there's p minus 1. So this is meant by divergence on the light cone. So if x and y are light-like separated, the chi squared tends to 0, and therefore this term blows up. And now I have to demand this equation order for order. And in fact, so what we can do is we can basically so choose a vector u so u in H so that psi u is supported away from x, or maybe psi u of y, but let me write it like this, is supported. so away from x. So this just means in this picture over here, if I have my x here, I just want to pick up psi u, which is supported not on x. So for example, I could have support here, right? This could be the support. And physically, this is this corresponds to basically choosing an ultra-relativistic wave packet, but this is just like interpretation. Okay, and why do we choose this? Well, what happens then is the following. So if this is not supported at x, then I know that there's basically, so this integration here is basically, so I fix x, so I integrate, first of all I integrate y over all of m, but then this integration of course reduces to the support of y. And so what basically happens is that, how should I say this? Maybe let me write it down and then explain it. So then star reduces to the following equation. So basically, the only thing, so the right-hand side, we have seen this. This is continuous. It's always continuous. Okay? So if the left-hand side diverges, and I'm checking order for order, as long as I'm working with the divergent parts, I can set the right-hand side to 0. And then furthermore, if this is not supported as x, the only contribution basically comes from, if you like, the parts of Q which connect x and y. So basically what I end up with is Q of xy 0. This is the equation we want to look at, evaluated weakly on the white light cone. Okay. So what does it mean physically? So it just means basically the equation which I can consider is I just take a look at this Q, which I've written down above, and I just take a look at the divergences on the light cone, at the divergent parts, and then, so basically it's enough to check whether those divergent parts vanish. That's basically what this equation implies for this choice of psi. So this is, if you like, a special case of this equation, because it's this evaluation weakly on the light cone. And this is referred to as testing with null lines. What's it called? Testing on null lines. Testing refers to the fact that, I mean, it's just like you can, so if you have a function which diverges in certain situations, you can test it by integrating it with a function which has a better regularity properties. Testing, and here we just do it on null lines, Okay, in case I've lost you so far, let me just say, so the only thing you have to remember now is that we have to test this thing weakly on the light cone, just 1 second, and that the only thing we need for that is really the eigenvalues of the closed chain and the spectral projectors, but primarily the eigenvalues of the closed chain. Okay, yeah, question? So in this case, it would be the same. This is the same because of this correspondence. So you can either work on the CFF side, and then it would be the CSF light cone, or you can work on the physical side, then it would be the physical light cone. Because like, so I'll talk later about regularization, but all of this is always sort of, we have to do what we want, what I outline now with regularization. Hmm? Yeah. Yeah. Yeah, it's very good. Yeah, yeah. No. So I think we had this question also 2 years ago. So we just used the word correspondence as a rough indication of some like identification which is mathematically rigorous. So I'm just saying how we use it. Yeah, yeah. Okay. So there's causal perturbation expansion is the next part. So okay, so I hope I have convinced you so far that we need the fermionic projector. So we need the fermionic projector of variations of Minkowski vacuum. So that's what we need and what we want. And this part is like a first step to get this, the causal perturbation expansion. And remember just so the fermionic projector of Minkowski vacuum, well, you've seen this. So this had this form, P of xy. Felix has written it down. So this is just the Fourier transformation d4k divided by 2 pi to the power 4. This is all a spin dimension 2 right now. And then you have this k slash plus m. And then you have this delta of k squared minus m squared. And then you have this theta function of minus k0. And then you have this, like, if you like, to carry out the Fourier transformation. Okay, so this, if you don't remember, this was what Felix has written down like this. So if you're in Fourier space, you have this lower mass shell. And this is just this integration over the lower mass shell, if you like. This is the fermionic projector of Minkowski space. This is the Dirac sea, okay? This was like a central ingredient. And what we want to do now is we now want to know, or like in order to, well, let me just clean the board and then I will. Oh yeah, sorry, there's a diff, yeah. Yeah, okay, you know it doesn't go. So the good thing is we already made it to page 100 of the blue book by now. So approximately. Okay, now we want to construct a fermionic projector of perturbations of Minkowski vacuum. So what we study now, so we want the fermionic projector Pxy for, let me just write it like this, for the equation, or an equation of the form like this. I d slash, it's just the Dirac equation, minus b, did we write it with minus, plus b, minus m, yeah, and then let me just put a psi here maybe, is 0. The essential ingredient here is this is unspecified, yeah? So we want a general expression, so maybe I should say we want a general expression. So why do we want this? So we want this because the fermionic projector, so how to say this? I mean, so basically this is just the sort of perturbation we take into, we'll take a look at now. A perturbation in terms of an external potential, and constructing the fermionic projector then basically allows to construct a causal fermion system. And this is always this shortcut for what happens in the background. This we consider perturbation of causal fermion system. This perturbation is of this form, for example. And then we could construct the corresponding fermionic projector from the causal fermion system, express it in terms of wave functions, and then we would end up with the same object. And I think in order to not, so I wanted to give some details about how to do this, but I think I will just sort of indicate the result. And this is like also, like all of this is a lot of work, basically. So the result looks like this. So, I mean, the result is something like this. And this is why, result. And again, the fermionic projector, you can interpret this sort of as the Dirac sea. And this is why the Dirac sea plays such a prominent role in this theory. So the result is something like this. So it basically says that this fermionic projector, or maybe I will not even write down x and y. So this has a form which looks like this. And maybe I should just say one word. And so the reason you can do this is sort of what this is this basically says you construct a vacuum for an arbitrary external potential. And in general, like if you just do physics as usual, this is not possible. There's this external field problem, which basically tells you if this external potential is not constant in time, then some particles and antiparticles will get mixed, so there's not a good notion of vacuum. However, it's part of the things which Felix, I mean, if you like, found out, that if you require a certain causality conditions of the Green's functions of this Dirac equation, then things are unique. And this is what you utilize here, but for time reasons, I will not go into this. So, but basically what you get is you get an expression like this. So first you have a summation over k going from 0 to infinity. It's like a perturbation expansion of the fermionic projector belonging to this equation. And so this is the perturbative way, and there's also, I should say, a way to do this non-perturbatively. And then this is basically, then you have a summation which goes from alpha to 0 to some alpha max. So this is just a number depending on k. And then what you have is you have a constant, c alpha, a little c alpha. And then you have, let me just write it like this. And then you have a structure like this. This is C, big C1 alpha. Then you have the external field. Then you have big C2 alpha, and you have the external field again. And so on until you basically end with C k plus 1 alpha. Okay? And here, this is just a number. So this is, maybe let's write it like this in R. And those terms here, those C's, they're now, I've written them as placeholders, basically. They're either of the following. So they are, let me just write it in words. So they could be the Green's functions. Since I haven't written them down, and maybe I should write off this Dirac equation with external potential here. Green's function of this Dirac equation. Or, and I will just, I mean, don't worry too much about if you don't know what this is. And I'm really cutting over so many things here, but this was the idea behind this lecture. Or they could be fundamental solutions. So for the Green's functions, they will just get the symbol S, Green's function is S. In fact, it's a combination of advanced and retarded Green's function or fundamental solutions. And again, don't worry if you haven't heard this term before. So, and I will just denote them by K or P. So this is a combination of the advanced and the retarded Green's function. So advanced plus retarded. And so just to so first terms, how do they look? To give you a feeling about this. This is really, so P is, the first term, for example, so this is equation 2, 1, 70 in Felix' book. So this would be something like P minus K divided by 2 minus S. Then there's the B, and then there's a P minus K divided by 2 again. Just to give you a feeling, minus P minus K divided by 2, and then there's a B, and then there's a S, and then there's terms of order B squared. Okay, so just to recap, so what we want is, we want the fermionic projector of perturbations of Minkowski vacuum. So then we take a look at those perturbations, and then there's this method, and it's called the causal perturbation expansion, and this basically tells you, well, you can construct a unique object perturbatively, but there's also a non-perturbative way to do this. And then it has this structure, and for example, the first term looks like this. So this fermionic projector is really given in terms of the fundamental solutions and the Green's functions of this Dirac equation over here.
So what is this S?
So this is this is the Green's function. Yeah. Oh, this is also supposed. They are both supposed to be small s. So the small s would be something like 1/2 the advanced Green's function plus the retarded Green's function. Yeah.
Just a remark about fundamental solution, you always mean like solution of the homogeneous Dirac equation. For example, the difference of the two Green's functions is one fundamental solution.
Yeah.
And the other one is the one where you have plus or minus
Yeah.
one on the
Yeah.
plus one on both.
Yeah.
Maybe another remark on so this perturbation expansion is this kind of the standard perturbation expansion in an external potential. So just like tree diagrams. The only thing which is not quite standard is the whole combinatorics. And this comes from some normalization conditions which we need to impose and so on. But maybe that's more technical these days.
So in Dirac C picture, speaking, there is no backwards projection Minkowski to Dirac C. And we have the perturbations. So there is at the level of Dirac C, there is no fermions, they move backwards.
There are, because there is this, S is like the mean of the advanced and retarded. So both advanced and retarded Green's operators come up. This means that things are kind of perturbed moving to the future and perturbed moving to the past.
So the causality is not both at the same time.
Yes. So there's no distinguished line direction.
No distinction.
So and again, so I know I have even skipped about things which I wanted to tell you, but I mean there's not so much time. And in general, I wanted to skip over many things anyway. So don't feel uncomfortable if you don't know really exactly like the meaning of this thing. The message is here just there's a way to construct a fermionic projector for any perturbation which is given by an external field in the Dirac equation of Minkowski spacetime. This is the message basically. Could have just written it down probably. And so now we have this, and the next thing would be the a thing which is called light cone expansion. Yeah? Question? Okay, so as I've said before, the things diverge on a light cone. Where's the question? Here, sorry, yeah.
We do this perturbation on the Causal Fermion system, and we see what happens
Yeah.
on the left side or the other right.
So my point of view would be this. So actually, So in my point of view, I would say, so we want to carry out so it's, as I said, it's like a shortcut. So we want to, so basically what happens in the background is a perturbation on the causal fermion system side. However, because of this correspondence, we're free to consider only the physics side. So this game here is really like for physics as you know it. So you're really on Minkowski space, you have the Dirac equation for psi on Minkowski space. But this is only possible because this mechanism which guarantees that whatever is done on the causal fermion system side corresponds to something on this side.
So what is the starting point of this perturbation?
Minkowski vacuum. So if B0 is a starting point, and you see it's a perturbation expansion, so this K here tells you how many B's there are. So there's a term with 1 B, and there's a term with 2 B's, as we had it here. Yeah. Okay, and so let's talk about this light cone expansion. So P and S have, as I said before, and Felix told you, have singularity structure on light cone. So this just means they diverge on a light cone. And let me think, maybe I can abbreviate, and so basically what we have to do is we have to expand. And maybe I should say here, I forgot to say this, those are like operator products, right? So this would be something like, for example, S, B, S. This would be something like, so maybe let's write it like this. The integration of D for Z. And then I have here, I mean, it's just something S of X, Z, times B of Z, times S of ZY. So SBS. So this is SBS of XY. Just a short. So this is sort of, those things are always, this X and Y dependence, I just didn't write it down here. But this is still there. Yeah, and so that's what I'm saying. So we have to expand this P we have just found and the different orders in this perturbation expansion. We have to expand this in orders of this psi squared. So this is the same as y minus x. And squared always means with respect to Minkowski inner product. So maybe let me just write it like this. Okay, so that's what we have to do. And let me now see how much details I will tell you. So let me just give you the result again. So it turns out that there, maybe what's good to say. So let me just say, it turns out that there's a way to do this. And this is really like quite complicated in my opinion, like how this actually works. But there's a way to systematically carry out those things in perturbation expansions. And I think maybe one thing which I could mention, or I could show you, I brought 2 slides just to give you a feeling about how those things would work. So maybe this is a good point to present the first slide. Yeah, not really, but okay. So the problem is that I always have to skip over so many things. So maybe let's do it in a minute. I have to skip over so many things that it's really hard to even. But so basically, let me just remind. So the vacuum fermionic projector can be written like this. So P of xy. No, there was just a term which I haven't defined yet. Yeah. So this is like basically I d slash, let me put it like this. You can write it like this. So this is a claim or just a statement. Tm squared. Or let me just Tm squared of xy. Okay, if you compare, we had it on the board somewhere. So, but it turns out that, so with Tm squared, and this is just the part which, like in this, so this is just given like this, of x and y. This is just given as the integration. So it's again a Fourier transformation, 2 pi to the 4. And then we have just the part which we except for this k slash plus m. So we have delta, and then there's k squared minus m squared. And then we have this Heaviside step function k0. And then we have this e to the minus I k x minus y. Okay. So this is just a statement that you can write it like this, because this will just act on the exponential over here. And why is this important? Because this Tm squared is really, so it turns out that, let me just say, maybe there's a modification of Tm squared such that the following objects, so I just basically take the derivative with respect to A, and now I'm just going to take the nth derivative of T, and then I put an A here instead of the m squared, and then I put reg here. So this means regularize. This means I've subtracted something which doesn't have a nice behavior on the light cone from this quantity here at A equals to 0. And those things here are is of order, if I'm not mistaken, and now what we have here, xi squared to the power of L minus 1. So this is really, so those things here are of this order on the light cone. So this means, and maybe I should say, so this is precise. I mean, there's a precise notion of what this actually means, and I don't have time to go into this, but this is section 2.2.1 in the book. What it actually means to have a divergence on the light cone. And this thing we refer, like this thing has we just call this thing TL, okay? And this just means, so the reason why I introduced those objects is because you can now expand the fermionic projector in terms of those TLs. You can write it down in terms of these TLs, and this is a light cone expansion. I'll do this in a minute. But the message is here just this object, basically divergence of this object on light cone or not, this object is just proportional to xi squared to the power of L minus 1. So for example, if you put 0 here, it's divergent on the light cone because it gets, so for example, T0 would be proportional to 1 over xi squared. I hope this is correct. And then, of course, there's smooth contributions. Okay, now I can tell you what I wanted to tell you next. So maybe just one more thing. So again, the idea to introduce those objects T here is really to sort of be able to control this divergence on the light cone. And this is not something which we don't want to have, but it's something which basically is the essential ingredient of this divergence in this analysis. I mean, just you analyze this Q order for order on the light cone, and then you find what you find. And I'll show you a little bit just in a minute. Sorry? Yeah? I don't know. What's the difference? So now you tell me. I don't know. So it's like, yeah, like this one would go as 1 over xi squared, but then there could just be 2. Like if I calculate these eigenvalues, I could get 2 of those factors. So I'm 1 over xi to the power of 4. So yeah. Yeah. Absolutely, absolutely. Ah, that's what you mean. Yeah, exactly. Yeah, it's coming up in 1 minute. And I can just I can sum up the last part. Oh, that's not so clean now, but I can sum up the last part in regularization words anyway. So what it turns out, or what you find, and then I'll show you the slide, is just you find basically that this fermionic projector can be written like this. So this is like the result of this light cone expansion. So you basically find P of xy can be written as a sum from n goes to 1 to infinity, and then you have something, and that's why I wanted to show you the slide. They're called phase inserted line integrals. That's a name. And then you have them, and you have one of those, or several of those, and then you have one of this Tn, what I've just written down. And this is dependent on x and y. And then you have smooth contributions. And we don't really care about the smooth contributions, because what we want to do is we want to take this fermionic projector, plug it into the closed chain, calculate the eigenvalues, and then see what are and then see what has to be 0, so that each order on the light cone vanishes on its own. Okay, and just to basically, and that's what I wanted to show you the slide. So I have 2 slides basically at this point. So one slide is really just to give you a feeling about sort of the things which are involved in this phase inserted line integrals. We can't define them rigorously at this point. So this is basically just the first slide. Maybe it's not even so okay. So what this slide basically just shows you is, so we use a certain notation, and this is the notation we use in, so it's just the first part of a theorem which I wanted to show you. No, I think it's not impossible. Yeah, I can just make it sharper. Yeah. Yeah, that's a good idea. Yeah. So this is just to show you a little bit of the equations which pop up. So the first equation is just a shorthand notation for a certain integral. So if I have if I have those square brackets and a function f, and I integrate with respect to z, this just means I basically integrate from x to y. I basically means I integrate over the how do you say the geodesic from x to y. And then we have those shorthand for those derivatives. This is just multi-index. Then all I wanted to show here is that when you do those perturbation expansion, so the sort of thing, so this is a theorem, not a result, but this is a theorem on the way. So what you get is you get combinations like this. So you get those integrates, and those integrals, and they're particularly over those, if x and y are on the light cone, they're over null lines from x to y. Yeah? And then what you have here, so the v's, they are basically, as written in bold here, they're basically some of the potentials, which you, like some of the parts of B. So in this case, the theorem, for example, is for this B as specified here. So this would be chiral potentials. And then, so what you basically get in those terms, which add up to the fermionic projector, are derivatives of the potentials, and they're contracted in certain ways. And at the very end, you have this S, and this S is basically the same thing as a T. So I just wanted to give you some feeling of sort of the structure involved. But maybe a more clear picture is the next slide. So this is basically a perturbation. Let's start here. So this is basically a perturbation expansion, if I'm not mistaken, also for the chiral case. And we have 2 terms which I'm just going to show you. So first of all, we have here the field strength, as you know it, yeah. And we have here the chiral current of the corresponding field. And so what this formula, what you see here, and this I should say is theorem, or you can find this in Appendix BB, Appendix B2 in Felix' book. You can find exactly this. And so basically what this is telling you is, so we now took the fermionic projector and we're now doing this light cone expansion. Why is this a light cone expansion? Well, because what I've written on the other board is that those T's, yeah, they're exactly of order psi squared to the power of T of, so I mean, they're divergent on a light cone, just as I've written down in a minute. So for example, this term here, you will get a 1 over psi to the power 4 from the first term times a factor psi slash. So this is just this perturbation expansion, this light cone expansion carried out for the P. And what you see is that the terms which you need in the Young-Mills equations, they pop up here. Yeah. So for example, you have the field equations here, the field strength here, and you have other derivatives of D here. And so this is just to say, you see those in this light cone expansion, you can see that the different terms which add up to the Young-Mills equations later pop up.
What's happened with singular T? They remove.
Sorry?
What's happened with singular T in the perturbation series?
What do you mean with singular?
So some keys are on light cone.
Yeah, this is a perturbation series in terms of the light cone. And you see this because you see here's a T minus 1. So that's more divergent than the T0. And that's more divergent than the T1 and so forth.
I mean the contribution. When you say more divergent, what is the contribution to the perturbation series? You have no contribution?
So I don't understand the question, I'm sorry. So I'm just saying the T's diverge on the light cone, and this is an expansion of the P in terms of the T. Therefore, it also is also an expansion of P in terms of light cone. So you see here the divergent parts of T. And I'm showing you this formula because here you see nicely how elements which you later need in the Young-Mills equations pop up in this light cone expansion.
Divergent part, they are not finite or finite.
No, they're divergent. Yeah, yeah. Okay, and so we're almost done. Yeah, absolutely, yeah. Okay, and so now let me just show you, let me just show you one more thing, or basically just mention one more thing, and then we're done anyway. So this is what is called the formalism of the continuum limit. So this would be part 5. And I will not really tell you what it is, I will just mention what it is. So this would be the formalism . Okay, so the point is, we have talked about before that the stuff not only is it so that in order to multiply, for example, two fermionic projectors, we need a regularization. And this is how you deal with the regularization. So maybe let's write, so need regularization. And so far we haven't considered this. And so one way to motivate how do you deal with this is basically, so a general regularization can be accounted for, and this is this formalism, but that this is possible is basically a result, by just basically replacing factors of MP, so M was the same thing as Y in the slide right now, M times Tn, by replacing those by basically MP, and now this is just a new notation, so you modify those T's. So you would have an N here, and you would put a P here. Yeah, so you modify, so I've told you what those T's are before, and now you see that when you introduce a regularization, you can modify those T's. And there's a sort of this formalism, just gives you computation rules for T's, for those Tn, and this just means, this P just means they're now modified. And those are valid for for any, or maybe I could write for any good or sensible regularization. And this is the reason why Felix basically, so why the results of the continuum limits or the structure of the equations which pop out are independent of the regularization. Because for any regularization which basically has the right structure means it's compatible with this vector scalar structure of the fermionic projector, you can show that those computational rules are satisfied, and then you just use those rules to get results. And let me see if there's anything else I wanted to say. And maybe just to give you, I don't know if it's really sensible. I mean, just to give you one example. So for example, there's something which is called the I epsilon regularization. Which just amounts to replacing the t in the fermionic projector by t minus I epsilon. And just to give you an example, so in this case, I would really have the t0 would actually be described by a quantity which, just to give you a little bit of intuition about it, 8 pi cube, and then I have 1 over, now I have 2r, and I would have t minus r minus I epsilon. And then this would just be the first term, and then I have higher contributions, which are of t minus r, order t minus r divided by r, and then I have higher contributions, which are of order epsilon divided by r, where epsilon is the regularization length. And now you see that now this thing is, after choosing this regularization, this is now a smooth function, because t and r are real, but here I have this pole, I've moved this pole to the complex plane. Okay, and maybe all I should just say is, for this whole thing, just look at section 244 in Felix's book. And now just to wrap it up, so basically, sixth part is get to physics. So this just just to wrap it up again. So what we have is basically sections, I don't know, 2 till 5. What did they give us? Well, they gave us an expression for a perturbation of the fermionic projector with general regularization and arbitrary, that's very important, external fields. Okay, arbitrary external field. And what we can do now, we can now plug this in. So we can do this to basically calculate, let me say it like this, variations of the eigenvalues of the closed chain. Okay? So we need all of this to calculate those variations. And then we can basically check if q of xy is equal to 0. It's like order for order, maybe I should say order for order on the light cone. And basically, this is not true in general, depending on B. And then the physics really pop out, and this really corresponds to equations for B. Okay? And this is basically the whole idea so behind the light code, the continuum limit. And really my goal, as I said, so it was neither to just give you a result, you find this in the book, but my goal was really to sort of give you, sort of introduce you at least a little bit to the terminology and to the terms which appear. And I hope with sort of this outline, you can find your way in the book. And I should say, so two things. So first of all, if you want to know more, as I said, like a lot of lectures in the last spring school, which are on YouTube, were about this. So you can just watch them and you will recognize all of the different parts which came up here. So in particular, for example, if you would like to see a specific example, how this works in a specific example, you can watch lectures 8 to 10 of the last spring school. So we've talked about a system involving neutrinos in this school, in those lectures. And last but not least, it's just an invitation to look at Felix's books, and I should say, well, this part is actually what is like the long part. So this is, I don't know, pages, what did you write it, 170 to 350 in Felix's book or something like this. This last part, to really carry it out. But nevertheless, I mean, have a look, and I hope now you understand at least a little bit the terminology. And I should say, Felix will later add some remarks in his own lectures, and also say a little bit about the question of the status of the Dirac equation in this whole approach.